Hello everyone, welcome to my channel Chemistry is Fun. Today I have come with the topic shapes of atomic orbitals. Now in this we see that if we have Schrödinger equation of atom and if we apply the Schrödinger equation to atom, we get some quantum mechanical model of atom. See, we know that Bohr had given the concept of orbits, but it can't be experimentally demonstrated. An atomic orbital refers to one electron wave function, and it can be explained with three quantum numbers. Principal quantum number represented by n, azimuthal quantum number represented by L, and magnetic quantum number, that is magnetic orbital quantum number, represented by M. We also know that in the atoms, the electrons can have only certain values of energy. So we can say that the energy is quantized. We can also explain about the probability of finding the electrons at specific region in an atom, and that region we specify as orbital. Now inside an atom, the electron state is given by atomic orbital wave function. The probability to find an electron inside any atom will be proportional to square root of the orbital wave function. That is, we have orbital wave function, and if you take the square of that, it can explain to a certain extent about the probability with which we can find the electron. Now this is called as probability density, and this is the representation. This value is always positive. Probability density is the probability per unit volume. Probability per unit volume is known as probability density. From this value we can predict the orbital, that is the region around nucleus where probability of finding the electron is maximum. In case of 1s orbital, the probability density is maximum at the nucleus. In case of 1s, near the nucleus there is maximum probability, okay? But in case of 2s orbital, the probability density first decreases, then it will increase. So as we see, as the value of n changes, the probability density also changes. Now where the probability density is 0, that region is called the node. The place where probability density is 0, that is called the node. We have a concept of azimuthal quantum number. Azimuthal quantum number determines the shape of the orbital, whereas the orientation of the orbital is given by magnetic quantum number. So if the orbital is designated by ns, as just now I told you about the node, that is the region where probability density is 0. If the orbital is designated by ns, when the orbital is designated by ns, number of nodes is given by n minus 1. If the orbital is designated by ns, the number of nodes is given by n minus 1. So in case we are considering 3s orbital, value of n is 3, so the number of nodes will be 3 minus 1, that is 2. The shapes of the orbitals can be expressed by boundary surface diagrams. Boundary surface diagrams. So s orbital, you see, this is the shape of the s orbital. The pa orbitals can be, there are three types: px, py and pz. They are along, if it is along x axis it is px orbital, along the y axis it is py, and when it is along the z axis we term it as pz orbital. So by the boundary surface diagrams we can explain the shapes of the orbitals. Now the probability density, whose representation I have shown, that will be constant. Now if you compare the shapes of the s orbital, as the value for n increases, the size of s orbital also will increase. So we can say that the shape of 4s orbital will be greater than 3s, that will be greater than 2s, and so on. For the p orbitals, the nucleus will be at the origin. The p orbital, as we can see, there are two lobes. The place where the two lobes are touching each other, there the probability density function is 0. This place where the two lobes are touching, this area, the probability density function is 0. Here also we can say that size wise 4p will be greater than 3p, that is greater than 2p. Here the number of nodes is given by n minus 2. So in case of 4p orbital, 4p, there will be 2 radial nodes. So number of radial nodes for 3p will be 1. 3 minus 2, 1. So for the radial nodes, we can use the formula n minus l minus 1 radial nodes. Radial nodes can be represented as n minus l minus 1, whereas angular nodes is given by l. Angular nodes can be represented by l. Next, what we have to see is the electronic configuration. Now we know that the electrons are filled in increasing order of their energies. Smaller the value for n plus l, smaller will be the energy. So we can see that the order of filling of electrons can be given as, first 1s is filled, then 2s, 2p, 3s, 3p, 4s. After 4s, 3d orbital gets filled. So this 3d orbital filling takes place after 4s. All the transition metals will be pressed here in the 3d, 4d, that is the d block elements. After 3d filling, 4p filling will take place, then 5s comes. So if you see the elements, if you consider one or two elements, like in case of hydrogen, it is 1s1. In the 1s orbital, 1 electron is there, 1s1. Helium, 1s2. 2 electrons are filled in the 1s orbital. They are having opposite spins. So in my next video, I will be discussing in detail about the electronic configuration and the rules which help to decide the filling of the electrons. Thank you for watching my video. Please subscribe to my channel so that if any new video comes, you will get the notification. Thank you.